Assalamu alaikum. Good morning, everyone. Can you hear me? Is it loud enough? Okay, thank you. So let's just start the class. It's already 8:15. So today we are going to do some mathematical calculation for the theory class you have already done, which is artificial neural network. And let's just recap something. So, some basics terms in artificial neuron is like input signals, some weights, and activation layer, a threshold function. Using this is the general diagram we work with neural network. So in the neural network, there's a perceptron. Perceptron is when you have one neuron only. So, a simple neural network, you can say a perceptron. So, um, single layer neuron. So, this is the overview of perceptron. And to do the perceptron, this is the algorithm. In this algorithm, there are basically 6 steps. First is to initialize the weights and then do the forward training for all the data we got. And in during the training, first we calculate the net input. The formula is bias plus summation of xi and wi, and based on that we decide on our output using this formula. If net is greater than 0, the out will be 1. If net equals to 0, the out will be 0 too. And if net is less than 0, the out will be -1. Next, we will check whether our out is matched with our target value or not. If it doesn't match, we need to update the weights and bias in our network. So to update the weights, we will use this formula where W old is the last weight we have used, and sum it with the here alpha is the learning rate and y is the target value and xi is the input. Similarly, for the bias, the equation is bias old plus learning rate into target. And the stopping condition is if all the output equals to our target value, we will stop our algorithm. So this is the question you will get during the exam. Here there will be given a table consisting of some input and a target value. So you will be told to do the train this perceptron or do the calculation. You will be given to do that. So in the question you will be given a table, you will be given the learning rate, and you just need to follow this step to do the calculation. Clear now? If you have any confusion, stop me and I'll repeat again. Okay, so to solve this problem, what we need to do is first creating table, a table like this. Here I have first I have written the things given in the questions. I have entitled it as given. What's given? input x1, x2, learning rate, and target y is given here. X1, x2, and y. It's -1, -1, here -1, and -1. So you will be given these inputs and target y, and based on that, our first step is to initialize all the weights to 0, and learning rate will be given as I've mentioned 1. So we have to initialize all the weights, and if you have bias, you have to initialize the bias too. So uh, initially we have taken the weights and bias and make it 0. Initially it is 0. Then we will calculate the net, step 4. The formula for net is bias plus summation of xiwi. Here xiwi means that for this row of data, xi where I will be 1. So this will be like x1, x1, x2. And for the second row, it will be this will be x1, x2, but this you can say this will be x11 and w11 for the next row, and for the third row it can be like it can be x1 2 and w12. You can denote it like that. It just means that for this formula is a loop, right? We have to calculate for all the weights and for all the inputs. So summation, it's a loop, so you have to calculate for all of this, for all of these weights and inputs. So the formula I have already written here. It's uh, okay, let me just simplify this a bit. Okay, bias will be the same, and we have to calculate x1 into w1 plus x2 into w2. Okay, this will be the formula for calculating net. So if we use this formula, you can see I have written 0 for bias, and as we start, this -1 is x1, and multiplying it with 0 because our w1 is 0, then plus again x2 is -1 and multiplying it with w2, which is 0. So we get 0 for our net. So the condition is if net is equal to 0, the out will be 0 too. So I have written 0 for out for this first row of data. Now we will decide whether we need to update the weights and bias or not. To do this, we'll check whether our output is matched with our target value. So as you can see, it's 0 and it's -1. So -1 not equal to 0. So we need to update our weights and bias and do the calculation again. So the formula for updating the weights and bias is like this. Weight old plus learning rate into y into x. So 0 is the old weight plus 1 is the learning rate, multiplying it with -1, which is our target y, and then multiplying again with -1, which is x1. Similarly, we will calculate w2. This is new w1 and this is new w2. So for the formula is same, just the these two variable, these two part will be changed. This will be sorry, then only the last part will be this will be x2, and we will get 1 for new weight w2. And for the bias, We have added like 0, which is old bias, plus learning rate 1 and our target value -1, and we get -1 for new bias. So using these new values like weights and bias, we will do the next calculation. So I write here that new 1, new 1, new -1. This is this 1, 1, 1, 1, 1 -1. This is the new value I have written. Okay. So again, we will do the net calculation, out calculation, and we will decide to update weight and bias. So if you have confusion, I can simplify this for you like using the column. So let me just do this calculation again. For calculating net, we need to add bias. Bias is this column. So we add the data of G3. G3 is okay. There is text, so it will not be added. So let me just uh, delete this part. 3 plus x1 is this column, A3, A3 into W1 is this one, E3, uh, plus x2 is B3, and multiplying it with W2, W2 is F3. Now, uh, uh, if we, that's not working. Anyway, this is the values we have like column name I have written. So if we do it manually, we will get what 0 and plus and -1 into 0 and plus similarly -1 into 0. So we will get right -1 into 0 is 0, -1 into 0 is 0. So we will get 0 for this row of data. Similarly for this one, we get -1 because our new bias is -1 and our x1 here is 1 and new w1 is 1. Now adding with new x2 -1 into new w2 here 1, so we get -1. So as this is -1 which is less than 0, so our output will be -1. As we can see, our target value is 1 and we got -1, which does not match. So we will update our weights and bias. So the new bias will be new weights will be 2 and 0, and bias will also be 0. Using these values 2, 0, 0 here, we will calculate the net out again. And we will see that we get 1 this time, but our target value, we get -1 this time and our target value is 1. So we will update the weights again, and this time we get 1, 1, 1. So using this 1, 1, 1, we calculate again, and we can see we found 1, which matched with our target value. The target is 1 and our output is 1. So 1 not equal to 1. This condition is not true because this matched perfectly. So we will not update the weights and bias, and we will stop here. because our stopping condition is that when out is equals to y, we will stop. So in this scenario, our main goal is all the out needs to match with our target values. So to do that, we'll start again with the same input and y with this weights and bias. Last updated weight and bias which give us our target value. The thing is, we first initialize the weights using 0 to start our program, and while after calculation we get a certain weight and bias which perfectly um, works for our network. So using these weights and bias, we will try to find all the outputs that matched with our target value. That's the concept here. So we will start second iteration using the last updated weights and bias, which is 111. This 111 we get from this iteration 111. So using 1, 1, 1, we again take the first input here, the similar one. Okay, again we start from the first input, then we get -1. -1 is also our target value. See, this is the like perfect weight and bias we have got because our output matched with our target. So here the target matched, so we do not need to update the weights and bias again. Using the same values we calculate for the second input, and we get the output 1 which matched with our target. So again we don't need to update the weights, and using the same values we get all the target matched with our output. So this is where we stop the program, and we can conclude that all the target match for the weights 1 1 and bias 1. And this is how we do the perceptron calculation. Do you have any confusion? Do I need to repeat any step here? Okay, this is one example, and there's another example here, which you can maybe madam will update the document in the column, so you will practice this one on your own, and if you have any problem you can ask in the group or you can text me. So you will not get your desired output uh, like this, like after first or second iteration. In some cases, uh, there can be a scenario where even after doing third or fourth iteration, you're not able to match your output with your target values. In that case, let me show you a file. Mm, okay. Like this one. Okay, there is also x1 x2 out. Don't worry about this data. The thing is, you can see there is 3 no and 1 yes. There is 1 yes, 3 no. So the scenario is same, that we are not getting no for all the um, output values. So you can conclude here that after second or iteration, if the output scenario is same, that no matter what you do you cannot match all the output with target, you can conclude that this program will go into infinite loop or endless loop. You cannot match all the target with y. You can conclude like this, and you don't need to do any calculation more than that. But um, uh, but uh, basically you will get output after two or third iteration. Okay, and if you don't and you say get the same output scenario, then you can stop. Okay, so if you want, I can share this with you, and you can take 5 minutes to look at this sheet, and you can ask me if you have any confusion. Okay. Any question? Okay, if not, we can move on to the next problem. So the next one is designing a neural network. To do that, uh, let's take a look at our lecture notes. Neural network. In neural network, some basic steps are these: data collection, normalization, network design, network testing, and network training and testing. So this is part of data from the most popular dataset, which is called IRIS dataset. In this dataset, there are four attributes. These are the attributes: sepal length, width, petal length, width, and this is the IRIS class. This denotes that if values are these values belong to the IRIS setosa class. These values belong to the iris versicolor class, and this is Berzinisa. Okay, so you will be given a table similar to this one, and the question will be like the question would be like this: for the given data set, do the normalization, network design, network training, testing. And so this is the similar table as you have seen in the lecture notes. So also there is another table which denotes the minimum and maximum value of the IRIS dataset. It's basically not involves these values. It These values are from the main IRIS dataset. So if you want to look at the main dataset, mm, see, yeah, this IRIS dataset is like you can see there is 150 rows, okay, in total 150 rows. So among these, this one is the sepal length, width, petal length, width. So this minimum and maximum value, the sepal length minimum means the minimum value from this column and the maximum value from this column. Similarly, for sepal width, this is the column, and the minimum value of this column is 2 and the maximum is 4.4. This is how these values are coming from, and it will be given in the question. What you need to do first is do the normalization. So why do we do the normalization? Because you can see the values ranges from like maybe this range is not that big, but sometimes in some data set the difference between values is really big. So for those types of values can slow down the neural network learning. So we do the normalization technique to keep our data in a normal range. Here the range is going to be between 0 to 1. In that way, neural network will learn efficiently. So the formula for normalization is this, where we can see v prime is equals to v minus mean a divided by max a minus mean a, and multiply it with new max a minus new mean a, and add it with the new mean a. So new max a and new mean a is the range you want your data range to be. So here we want the new max A is to be 1 and the new mean A is to be 0. So if you see, the 1 minus 0 is equals to 1. So basically you are multiplying this value with 1 and adding new mean A, which is 0. So this part of doesn't hamper this part of formula doesn't hamper our this part. So we will just calculate this part to normalize our values. And to do that, v prime and v, what v prime and v means, v prime is the new normalized value for v. And what is v? V is each cell in this table. Like, you have to normalize all of these values. So first you start with this 5.7. So currently your v is 5.7, and when you working with this, the v will be 4.4. Similarly 1.5 or zero point 0.4, these are your v value, and for each v we will calculate corresponding v prime, which is the normalized value for this. So to do that, first let's see. So v minus 4.3. So v will change, but these other things will remain for a sepal length column, because okay, let's just go to the table here. So I have taken the data given in the question. I have written it here at a length with iris class, and using this formula we will normalize this data. So first, 5 for this value 5.7. So 5.7 minus 4.3. 4.3 is the minimum A of this column, divided by maximum A minus minimum A. Maximum A is 7.9 and minimum A is 4.3. So 7.9 minus 4.3, and the output will be 0.38889. So similar to this, if this will be 1. How? If you see, the V here will be 4.4 minus new mean A for this column is 2. So 4.4 minus 2 divided by uh, max A minus mean A. Max A here is 4.4 and mean A is 2. So 4.4 minus 2. Let's see what we get for this calculation. See, it's 1. We will get 1. So the normalized value for this is 1. Similar to this, if you see, petal length 1.5. So 1.5 minus new mean A is 1 for petal length here. See, new mean A 1 for this column. So we will minus that 1. 1.5 minus 1 divided by max A minus mean A. What is max A here? Max A is 6.9 and mean A is 1. So 6.9 minus 1. If we take this value, you can say uh, we get 0.0847. Here it is 0.0847. So this is how we normalize the values. So using the same technique, you need to convert all of this value in a normalized form. And after that we will convert our class into numeric form. Why we need to do that? Because in the neural network all the calculations include numerical values, right? All the values, derivative and integration, derivation, all those include the numerical value. So we will get output as numerical value too. neural network cannot process this text data. So we just convert this text into some number. This is called label encoding. We are labeling, we are encoding the labels of our dataset. So suppose we can take it as our own, but for like easier, we have written iris setosa as 0, versicolor as 1, and virginisa as zero point 0.5. What will happen is, if I get output as 1, I will know this belongs to iris versicolor. If I get 0, I'll know this belongs to iris setosa. This is what label encoding is for. Okay. Any confusion in normalization part? Okay, let's proceed. Normalization is done. Then we will do is network design. So for the network design, there is so network design. There are four input attributes, which are these ones, like sepal length, sepal width, petal width, and iris class. Iris class is the output layer. So from four inputs, we get one output, which defines that what kind of iris we will get. So to do that, there is a figure. Okay, this is similar to this one, but if you want to look at some whiteboard or just paint. Okay, let's just design our neural network. So our input is four, right? Four attributes. Okay, here. So this is sepal length. Sepal length. This is sepal width, and this one is petal length. And this one is petal width. So using this, okay, and if we draw our network, from each input, this will first go to this neuron. So basically this is input layer and this is hidden layer, and this is output layer. This is output layer. So similarly all of the values will go to this neuron too. Okay, and so this is x, you can say, um, x x denotes input, and for each input there will be two uh, weights. Okay, because from each neuron it is going to two neurons, so weight maybe it's w11 and the next one will be w12, and after that from this neuron it will go to the final layer and we will get y. Okay, y is our output, and here we can say this is um x, new x, you can say new x, because this will become our new input and the weight here can be v. And similar, I'm not writing for each of these values, I'm just showing you the overall network design. So this will be our network. Okay, so our network design is done here, and after that we will start our forward propagation. Forward propagation is similar to the perceptron calculation we have done before. The thing is there is no bias mentioned in the question. So the forward propagation includes like doing the same formula like this one. Activation is sum of weight I into input I. After that we will just use activation function to turn on the neuron. The concept of activation function is if you say that maybe for iris setosa, sepal length and sepal width data is important. So, uh, but petal length and petal width is not important that much. So, what we will do is uh, we will activate the neuron only for x1 and x2, like for this uh, connection only. For the below connection, this neuron will not be activated. And how we can do that? We can do that using the activation function. So here we will use the simple sigmoid function from there. So if we start our training program, so let's just start the way we did for Percepton. And here first is input layer x, and where we are getting these values from, it's from the normalization. From the normalization, the first row of data is this one, 0.3881, 0.08, 0.125. So here 0.3881, 0.08, 0.125. So we are starting with first row of data, and input weight we have here initialized it with 0.1. We did not use 0 here is to, if we use 0 maybe the calculation will be uh, a step more than using 0.01. Point, all, every time when initializing weights and bias, this needs to be something close to 0. A small value will be good enough. We cannot use large values. Okay. So here we have initialized our weights into point 1, and then we are calculating our input net. The formula is same, sum of xi wi. There is no bias. In the Percepton there was bias, but we don't have bias this time. So here for the, like for x1, x2, x3, 4, first we will take v11, v21, v31, v41. Okay, so this is what maybe I've written wrong. V11, V21, V31, and V41. And if you take this data, you will get this value from 0.159863. You see 0.3889 is x1, multiplying it with v11, which is zero point 0.1, and then x2 is 1, and then x3 is 0.08, and x4 is 0.125. So this is the simple input net calculation. And for the net 2, the calculation will be same. Okay, there, this is net 1, this is net 2. If you see, this is net 1 and net 2, we have calculated net for these values. So net 1, net 2, and after that now we will use the activation function. Activation function, what's the formula for activation function? This is the formula: 1 divided by 1 plus e inverse y. You can see inverse x. Okay, this is for back propagation, sorry. Where's this? Inverse x for the input. So we have taken this net 1 value. Now we are calculating activation function. Z, we denote it as z1 and z2. So after activation, after applying the formula for activation function, we get the value this 0.539881, and the value is same because the input values are still same. Now we have to do again propagation, because now the these are the input and this going through the output layer. So we are doing for a propagation again. Now we have taken new weights, which are w1 and w2, initialized with 0.1. The similar thing we did before. It's z1 into w11 plus z2 into w22. So after multiplying and adding these values, we get 0.1079762. So we get our hidden layer net value. After that, we will do the activation function for hidden layer, and we will get 0.526968, just using the E inverse formula we have used before. So after that, we get activation value for our output layer 2. So what we've got is zero point 0.5, but our target is 0.0. Why? Because you can see for this value belongs to iris class Setosa, which denotes as 0, but we did not get 0, we got 0.5. So it did not matched. So we need to work again on this value. So to do that, now we will do back propagation. For back propagation, the concept is we will minimize the error, we will update the weights and bias to reach our target value, which is 0. Now to calculate the error, the formula is this. There's a formula in the sheet. What's the formula for? See, now we are starting back propagation. The back propagation includes transfer derivative and error back propagation. And derivative formula is this one, y into 1 minus y. And for the error, here, error, expected minus output into transfer derivative. Okay, y into 1 minus y into t is the target value minus y is the output we got. So if we simplify this step, uh, so first, let's just calculate the mean error. Okay, this is equation for calculating mean error. Mean error MSE. You have heard about it, right? MSE. There is mention about it here somewhere. I've seen mean error. Okay. Okay, you just find it on own. I'm not finding it. This is called MSE, mean square error. The formula is this: target minus y whole square. So our target is 0 and we got 0.52. So 0 minus 0.5, 26962 or 53928. Okay, let's just take this value. Okay, so if we do calculation for this value, we get okay, 0.77695. This is the value. Let's just take the 4 5 values here. So here it is. Okay, 0.277769. So we get our error. We've calculated the error. So in the question, the learning rate will be given. Now we have to calculate the delta y and delta z. What are these? Delta y is the output layer error and delta z is the hidden layer error. So after minimizing this error and updating weights and bias, this is how neural network works. So to do that, it's the back propagation step here. First step is to calculate error for each output neuron. This will give us error signal to propagate backwards through the network. Output layer error is multiplication of error value with activation function derivative. So this is the output layer function. This is the output layer function error. Okay, so the formula is really simple. Do not get complicated because there are superscriptive and subscriptive like UK. Don't bother. Just write y into 1 minus y into t minus y. This is what I have written: y into 1 minus y into t minus y. In the we are in the activation function hidden layer. Okay, so in this layer, y is the what we have got from the previous iteration, 0.5. Okay, let's just use this one: 0.526968. So y into let's just copy paste this value: y into 1 minus y, 1 minus y, and multiplication with t minus y. Our t is 0 minus y. So if we do this calculation, we will get these values. Okay, this value. Here. So if we do this calculation, we will get minus 0.13136. This is the delta y output layer error. After that, we can calculate delta z1 and z2, which is the error for our activation function in input layer error. Okay, this is what they have mentioned here. The after output layer, uh, okay, output layer, then we will calculate for the input layer also. Okay, for the input layer the formula is same, just summation of x, w and delta is what we have done before. We will just use the value here. So for delta z1, um, the formula is this: z1 into 1 minus z1 into v11 into delta y. Delta y is the value we get from here. So z1 is here, z1 into 1 minus z1 into v11. Maybe it's not v11, it's w11. Okay, w11. Uh, what am I doing is calculating error for this input layer. And where this input layer coming from? For this input layer, the weight includes is this W1 and W2, and we get output is this 0.52, and for 0.52 we get error is delta y. So we use delta y here. So for the Z1 we get error is minus 0.00326, and for Z2 we get the same values actually. So W2, this will be W2, and this is W1. Okay, so we have calculated error for this part of the network too. So after that, we will just initialize our weights. For the now we need to update our weights. To update the weight, we know the formula, right? We have done in the perceptron. Old weight plus learning rate into delta y into input. For this new v1, like new v11, the old weight is zero point 0.1, and learning rate is 1 already given, and delta y is here 0.13136, and input, what's the input for this one? The input for this one is this 0.388. So using this we get value for new v1, and similar for all these values we get new weights. So we have done the forward and backward propagation for only this row now. You have to do the similar calculation for all of these rows. And for the second row, if we take a new sheet, training for second row, okay, this okay, let's just take this first. Then here the input will be this normalization. Okay, these values will be the input here. Okay, x1, x2, x3, x4. 5 number. Okay, x1, x2, and x1, x2 values for second row is this 5.4, 3.9. Okay, we get our input. Now we don't need to initialize weight to 0.1 this time. The weight will be coming from these values we have updated in the previous iteration. So we just copy paste these values. Okay, this is the new weight for our second row iteration. So the process will continue as we have done here before. First forward propagation, and then error, and then backward propagation, and we do this for all of this row until our target matched with our output layer. So do you have any confusion until now? You can take 5 minutes, look at the sheet, and ask me if you have any question. These are really simple maths which will definitely appear on your exam. You just need to concentrate on the formula you are using. Carefully use the formula and think what you are going to find out, what you need. Just practice this math, so this will be easier for you during the exam. So if you have any question, um, take a look at the sheet and ask me. I'm giving you 4 minutes. Okay. Yes, please. Precision over for decimal. Uh, Maybe 3 to 4 after decimal point. You can, as standard, you can take 5 points, 5 digits after the point values. Okay, maybe, okay, 1 minute. Sorry, I did not get your question. Yeah. If you take the 5 digit, maybe you don't need to round it. Okay, just take the first 5 digit. Okay. Any more question, anyone? Any confusion in any step? You can also practice and then ask me in message or in the next class if you want to. So if you think no more questions Now we can end this class today. Okay, then maybe see you on the next class. Okay. Uh, Thank you, everyone. Assalamualaikum. Walaikum.
Inshallah, thank you, madam.
Thank you, madam.
Welcome.